So we were discussing about limit state method, and we were discussing about the limit state method fundamentals. We are moving further. See, I'll ask you one question. So if you want to construct a building, you are going to a civil engineer, right? You want to construct a building, and you are going to a civil engineer. That civil engineer actually, what he will think first, what he will think, or what he has to consider first. If I am going to construct a building, or forget about that, if I am going to construct a building, what I have to think first? What I have to think first when I start constructing a structure, or when I start designing a structure, what thing you should consider first? No, not stability actually. What is the first thing we should keep in our mind? I am expecting your answer. Before constructing a structure, before designing a structure, what is the first thing we have to consider? Yes, we have to think about for what it is to be designed. Exactly correct. We are designing the structures for taking loads. Right now, suppose we are constructing a building like this. It is a high-rise building. I don't know. I want to construct this building. Here it is a multi-story building. I want to construct this building, right? And before constructing it, before designing it, we have to go for design, right? Before designing it, we need to calculate how much load will be acting here on the structure. So to explain that, I will ask you one question. What are the different kind of forces, what are the different kind of loads acting in a structure? What are the different kind of loads acting in a structure? You already know this, right? Different kind of loads which are going to be acting in a structure are dead load will be there, and live load will be there. Live load will also be acting in the structure. Dead loads, yes, you are right. Dead load, live load, and wind load will also be there. Wind will also give some loads, na? So the wind load will also be there. And finally, earthquake load will also be there. Earthquake load or seismic loads. Earthquake load will also be considered in the design. So we have to consider these 4 different type of loads into consideration. See, Vishnuvardhan is saying that snow load, so it will also come into the picture where snowfall is there. So we are not going to consider that here, right? In India actually we are not going to consider the snow loads and all, right? So earthquake, wind load, those things are there. Of course those things are there. These are the loads which has to be considered for the design of reinforced cement concrete structures. So these are the various kind of loads. What is actually this dead load? What is dead load? The load due to self-weight. Suppose if we are carrying a beam here, we are having a beam here which is a reinforced cement concrete beam. This beam will carry some weight. There will be weight for this beam. No? So this beam, the weight of this beam is called our dead load, or the self-weight of the beams or self-weight of structure will contribute our dead load. Otherwise, if there is some any permanent live load is there, live load which is not movable, any permanent live load is there which will also contribute, which will also be considered as our dead load. What is the meaning of this live load? In this room, I am live load. Load which is movable. The direction or the direction of the load will be different. I will be here sometime. After some time I will be here. I will be moving here and there. Right? That is movable load. Load which can move. The persons in a building or the furnitures, all these things can move here and there. No? So the movable loads are termed and discussed under the heading live loads. Then wind loads. See, if it is a high-rise building, if the height of the building is very high, we have to consider the effect of wind load also. The wind load will also be, the wind also will be creating some loads in this structure like this. Suppose the wind is acting in this direction, it will be creating one force in that direction. So we cannot say wind will act only in this direction. The direction of wind is actually not predictable. We cannot predict the direction of load exactly. The direction and magnitude of the wind load will vary from time to time to place to place. Right now, so direction will be different in case of wind loads, similar to that of earthquake load, similar to wind load, earthquake load also. We cannot predict the magnitude of this seismic load. We cannot predict the direction of the seismic load. So we have to consider all these loads into consideration when we design a structure or before we designing a structure. The first thing as a designer you have to do is load calculation. You have to understand. You should know for what load I have to design this structure. Right now, for what load I have to design this structure. So please write down the heading design load and characteristic load. Design load and characteristic load. Design load and characteristic load. So this understanding this concept is very important. Suppose I am taking the same building and I am considering that is an office building. Usually or generally there will be around 100 persons will be there. There will be around 100 persons will be there generally in this building. On weekdays there will be around 100 persons. On weekends, on holidays maybe, there will be maximum there will be 10 persons will be there in the building. Understand this? Then usually or most of the time there will be 100 persons in the building, and in sometimes like on week of days and all there will be around 10 persons, a maximum of 10 persons will be there in that building. Suppose if some meeting or some other functions are there in this building, maybe around 1,000 persons extra will come, or around 1,000 persons will be there in that building. So these are actually the different kind of loads under various with respect to time. Sometime 10% will be there, number of persons will be 10, and usually most of the times the number of persons in this building will be around 100, and in sometimes in very rare cases due to some function or something the load and acting in this building is around 1,000 persons or 1,000 persons load is acting on the building. So for designing, which one will I consider? Will I consider this 10 persons load or 100 persons load or 1,000 persons load? Which load should I consider for the design? Can anyone tell me? Which person's load will I consider for the design? Yes, I know your answer will be 1,000. I'll come to that. See, if I plot a curve, if I plot a graph like this, in the x-axis I am going to consider load values. In the y-axis I am going to consider the frequency of occurrence of the load. In the x-axis I am going to consider the load values, different load values, and in the y-axis I am considering the frequency of occurrence of the load. And for 10% load, if I consider 10% load here, our 100% load will be somewhere here, and our 1,000% load will be somewhere here. What is the frequency of occurrence of 100% load? Will it be more or less? It will be more now, of course. Yes, the frequency of occurrence of 1,000% will be more, and the frequency of occurrence of 10% will be less, and frequency of occurrence of 100% is very high, and frequency of occurrence of 100% is very high, for 10% it is less, and for 1,000% it is very less. Right now, if you plot a curve like this, you will be getting a curve like this. You will be getting a curve like this, which is having the more frequency of occurrence. The 100% load is actually the most frequently occurring load in the structure. You will be getting a curve like this, right? 1,000% load is actually having very less frequency. 10% load is also having less frequency, but for 100% load will be occurring more frequently. So tell me, which one will I consider for the design? Will I consider 100 or 1,000? Will I consider 100 or 1,000? Varsha, and in the yes, you are right. Will I yes, I know your answer will be 100. Fine. The answer again, I have to explain it again. The answer is wrong. We cannot consider this 100% load for the design. We cannot consider 100% design load for the design. We cannot consider this 1,000% load also. Of course, we will not consider 10% load, which is very less, right? So we cannot consider this 10% load. We cannot consider this 1,000% load. Why? Because see, these are imaginary, right now. This is actually an imaginary condition. We don't know. See, we have not designed this structure. This 10%, 100%, 1,000%, those loads are not there in the structure. We are constructing the structure in the later stages. Now we are in the design stage. We are just thinking, okay, this much persons will be there in that structure. All these load combinations, load calculations are actually imaginary. Yeah? We can expect, okay, 1,000 persons will come. That is not exact value. Is it an exact value? No. Just like think about this load values. This design load, this dead load will be acting in the downward direction, or it is also called gravity loading. But think about the live load. We cannot exactly predict the magnitude of this live load in the structure. Sometimes more persons will be there, sometimes very less persons will be there, sometimes many number of persons will be there in that building. So live load can vary in magnitude. Right now, similar to that wind load, I discussed with you, the wind load, the direction of wind load will be different. The direction and the magnitude of the wind load will be varying from time to time, or from place to place. So we cannot just predict the magnitude and the direction of this wind load exactly. And talking about the earthquake load, similar to our wind load, the direction and the magnitude of the wind load cannot be predicted, just like our wind load. So I'm going to tell like this. You have to remember this. There is always some uncertainty involved in the calculation of the loads. There is always some uncertainty. We cannot just exactly predict the load which is going to be acting in a structure. There is always some uncertainty involved in the load calculation. So that because of the uncertainty present, I am going to use probability approach, or I am going to use the help of probability concept for finding the load which is to be considered for the design. And it is generally found that the variation of this load, the frequency and load relationship, follows normal distribution. It follows our normal distribution. You might have studied it in probability. It follows normal distribution. Please note it down along with me. Normal distribution. It generally found that the relationship between this frequency and the load follows normal distribution. You know what is the relationship? You will be getting for normal distribution, you will be getting a curve like this, which is a bell-shaped curve. For normal distribution, you will be getting a bell-shaped curve here, and in the middle you will be having the mean load, right? In the middle you will be having the mean load, right? You will be having the mean load. Now tell me, which one will I consider? Will I consider this mean load? That means around the mean of these loads, or will I consider this 100, or will I consider this 1000? Which one will I consider for the design? Will I consider mean of all the loads here, or will I consider this 1000, or will I consider this 100? I am not going to choose any of this. I am going to follow IS 456-2000 blindly. Our IS 456-2000 is saying that consider, after drawing this, or after considering this, or after considering the normal distribution curve with load on the x-axis and frequency of occurrence on the y-axis, consider a load value which is having around 95% of probability of not being exceeded during its lifetime. You have to consider a load value. This is the load value there. This is the load value. You have to consider that load value which is having around 95% of probability of not being exceeded during its lifetime. That load value which I am getting here at the 95% of probability is called our characteristic load. Characteristic load acting in the structure. So what is characteristic load? The load which is having around 95% of probability of not being exceeded. Which means that if in this structure, suppose 1020% is the characteristic load, which means that the meaning of that is 95% of probability is that the load which is acting on the structure is not greater than 1020% load. The 95% of probability is there, load acting on the structure will not be more than our 1020% load. Our IS code is suggesting to use the characteristic load, or IS code is suggesting to consider the characteristic load which is defined as the load which is having 95% of probability of not being exceeded during its lifetime. So you have to write it, characteristic load. It is denoted by capital FCK. It is the load which is having 95% probability of not being exceeded during its design life or during its life. Remember this, the having 95% of probability of not being exceeded during its lifetime. That is called our characteristic load. Now tell me, please respond, which one will I consider? Will I consider this 10? I will not consider that, right? Will I consider this 100? Will I consider this 1000? Or will I consider this characteristic load for the design? Which one will I consider? For the design of the structure, which one will I consider for the design? Tell me which one will I consider for the design? Yes, FCK. We cannot do that. Why we cannot do that? I know everyone's answer will be FCK, that is characteristic load. We cannot use that value for the design. Why? Because that load is having around 95% of probability of not being exceeded, right? So we were discussing about the characteristic load. I discussed it here. The load which is having around 95% of probability of not being exceeded during its lifetime, that is our characteristic load on the structure. But I asked you a question, right? So which one will I consider? You have given me the answer also. I asked you like this. Which one will I consider for the design? Will I consider this 100? Will I consider this 1000? Or will I consider this characteristic load? You people have, most of you, I think almost all of you has given the answer as characteristic load. I told you we are going to consider this characteristic load for the design. Or for design we are not going to consider this. Why? Because see the definition here. It is the as per the definition, it is having a probability of 95%. There is around 95% of probability of not being exceeded, which means that there is 5% probability is there in with which the load can be exceeded. Correct? Now 95% of probability of not being exceeded, but there is a 5% of probability of being exceeded. Now, so that is 5% is actually our risk. We are taking that risk. If you are considering this characteristic load for the design, I am taking a risk of 5%. Getting it? So we cannot, as a designer, we cannot take that risk in the design. So we are not going to take our characteristic load. I'll discuss that. See, if you coming back to this curve, coming back to this normal distribution curve, I told you this is our mean load. This is our mean load. That is the distance from here to the center is our mean load, or I am going to denote it as Fm. And if you might have studied it in the normal distribution, or otherwise you will study in future. For 95%, this is actually a 95% portion, right? For 95% confidence level, that's called confidence level. This value from the center, this value is around 1.65 sigma. This is a constant value. For 95% of probability, the distance from the center to that point is around 1.65 sigma. So we are interested, what is FCK? FCK is actually from here to, okay, right here, to this point is called our FCK, that is characteristic load. Can you make a relationship between this FCK, Fm and 1.65 sigma? If you see this figure, you can easily observe the characteristic load, that is FCK, is equal to Fm, that is the mean load, plus 1.65 sigma. Can you say like this? Fm plus 1.65 sigma will be our characteristic load acting on the structure. The characteristic load here will be equal to FCK, which is FCK is equal to Fm, this plus this. This portion for 95% of probability, this value here will be 1.65 sigma, and this is our characteristic load. The characteristic load, this will be equal to Fm plus 1.65 sigma. The characteristic load will be equal to Fm plus 1.65 sigma. Fm plus 1.65 sigma. For FCK is the characteristic compressive load, Fm is the mean load acting in the structure, sigma is the standard deviation. Sigma is the standard deviation. Right? Please note down. Are you able to hear me? Am I audible? Chinmay, Dhruv, Angit, Varsha. Yes. Then please note it down. Please note it down. Make it fast. Remember this equation. It is one of the most important equation. You will be getting questions directly. He will be giving you the mean load. He will be giving you the standard deviation. You will be asked to find the characteristic load. Sometimes he will be giving you the FCK. He will be giving the sigma value. He will be asking the mean load in the structure. Right? Yes, it's a very important equation. If you remember this graph, if you remember this figure, you can easily understand, you can easily remember this equation. Therefore, when we consider this normal distribution, we will be getting a curve like this. It's a bell-shaped curve. This is actually in the middle, that is around 50%. But as per our IS 456-2000, the characteristic load is that load which is having 95% of probability of not being exceeded during its lifetime. That is 95% probability is coming around here. This is 50. This is 95. This remaining portion is 5%. So this much is FM, that is mean load, will be our mean load. And for 95% of probability, this value here will be 1.65 sigma. 1.65 sigma, where sigma is the standard deviation. Sigma is the standard deviation, right? FM plus 1.65 sigma. Remember this value is also very important, 1.65. Sigma sin sigma is equal to standard. Yes, test action, we are right. Okay, FCK is equal to FM plus 1.65 sigma. Is the FM from y-axis? No, it is from the x-axis. We are considering the load in the x-axis, no? We are considering the load from the x-axis, right? Yes, this is coming in now. This is actually our FM value. This is actually our FM value. FM means mean load. You will understand this when we start solving a question. You will understand this. Okay. FM means mean load. FM means mean loads. Mean of the loads acting on the structure, right? Then I told you we will not consider this characteristic load for the design. Why? Because there is a risk of 5% is involved. It's a load which is having 95% of probability of not being exceeded, but there is a 5% chance is there with which the load can exceed this value. So we cannot take that 5% value. For that reason, for the design purpose, I am going to increase this load. I am going to consider a load value which is much more than this characteristic load. That load value is known as, anyone? That load value is known as design load. I am not going to consider this characteristic load for the design, but instead I am going to increase this load to by some factors, by some certain factor of safety. I am going to consider the load value which is much higher than this characteristic load. That load value is known as design load. This is obtained by multiplying our characteristic load with some partial safety factor. I am going to consider it as gamma F. Let's say gamma. This is our characteristic load and gamma F is the partial safety factor for loads. FCK is the characteristic load and gamma F is actually our partial safety factor for loads. Partial safety factor for loads. Partial safety factor for loads. Design load, or I am going to denote it as FD, capital FD. The design load FD is equal to FCK into gamma F, where FD is the design load, FCK is the characteristic compressive load, and gamma F is the partial safety factor for loads. You can ask me, sir, how to find this partial safety factor values? How to find this partial safety factor values? See, this FCK value, this partial safety factor is given by our IS 456-2000. These values are given in a table in IS 456-2000. We are going to use that values for finding the design load in a structure. Right? Yes, please note it down. So this is the same question used to design. See, it's tie-seam fires, right? For fires, actually, we are coming to that. After this, we will be discussing about that. Characteristic strength and characteristic load. Sorry, characteristic strength and design strength. Here we are discussing about loads, na? And in the next concept, we will be discussing about the strength. Characteristic strength and design strength. Okay? Right? I think I can remove this, right? As I have discussed, in order to determine the design load in a structure, we have to multiply the characteristic load with some partial safety factor for loads. The partial safety factor for loads are actually given in a table in our IS 456-2000. If you see the code, you can see one table there. But we have to remember this table. Why? Because these things are not allowed. That IS 456-2000, that code book is not allowed inside the exam hall. Na? So you have to remember that table for solving the questions. So we are going to discuss about that. Please give the heading partial safety factor for loads. 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 See, while discussing the partial safety factor for loads, as I told you, limit state method or limit state is discussed under two headings. First one is limit state of collapse and second one is limit state of serviceability. So we have to consider the partial safety factor for these two. I have to first consider the limit state of collapse. After that I have to consider the limit state of serviceability, and IS code is giving us separate values for these two. What are the partial safety factor for loads as per limit state of collapse? What are the partial safety factor for loads as per limit state of serviceability? So for limit state of collapse, what are the partial safety factors? See, in order to determine the partial safety factor, in order to discuss the partial safety factor, as I told you, we have different loads acting in the structure. We will be having dead load, we will be having live load, we will be having wind load, and we will be having the earthquake loads acting in the structure. We are not going to consider them separately. See, in a structure there will be load combinations, right? So there will be dead load, live load combination, or there will be dead load, wind load and earthquake load combination, or there will be a combination of all the three. So we have to consider the load combinations for the for taking the partial safety factor values. So in the first column, give the heading, give the first column load combinations. Load combinations. Consider from the first column load combinations, where we are going to consider various load combinations like this. First load combination which I am going to consider here is dead load plus live load combination, and in the second row I am going to consider a load combination like this: dead load plus wind load or earthquake load combination. And finally we are going to consider all the loads together: dead load, live load plus wind load or earthquake load combination. And the partial safety factor values. Partial safety factor values. Partial safety factor values for loads. For dead load, what is the value? For live load, what is the value? For wind load or earthquake load, what is the value of factor of safety? If I consider the first load combination, which is dead load plus live load combination, our IS code suggests the use of a partial safety factor of 1.5 for dead load, 1.5 live load. As we are not taking the earthquake load or wind load in the load combination, there is no need of considering our wind load or earthquake load combination. Then coming to our second one, dead load plus wind load or earthquake load combination, we have to consider a partial safety factor of 0.9 or 1.5. Here it is, actually we are not considering the live load here, so we don't have to mention anything about that. And for wind load or earthquake load, it is 1.5. And for our all the load combination, that is dead load plus live load plus wind load or earthquake load combination, the partial safety factors to be considered as per IS 456-2000 for limit state of collapse is 1.2, 1.2 and 1 point, right now. And again, that is for limit state of collapse, right? Now we have to consider limit state of serviceability. We have to consider the limit state of serviceability, and the load combination will be same: dead load plus live load, dead load plus wind load or earthquake load, dead load plus live load plus wind load or earthquake load. And the partial safety factor for dead load, live load, wind load or earthquake load will be like this. For the load combination dead load plus live load, for the dead load we have to consider a partial safety factor as 1. For live load it is 1. As we are not taking it in the consideration, we don't have to consider that. Dead load plus wind load or earthquake load combination, we have to consider 1 here, we have to consider 1 here. For all the 3 loads, we have to consider 1 value here, and here it is 0.8 and here it is 0.8. So these are the load factor values considered in the design, or these are the load factor values used to find the design load in a structure, right? You have to remember these values. It's very easy table actually. Just understand this load combinations. Dead load plus live load combination, dead load plus wind load or earthquake load combination, then all the 3 together. Dead load, live load, wind load or earthquake load combination. 1.5, 1.5, 0.9 or 1.5, 1.5, 1.2, 1.2, 1.2. Here it is 1, 1, 1, 1, 1, 0.8, 0.8. So remember it like this. Okay, you have to remember this. You can expect many number of questions, because if you see the previous year question paper, you can see many number of questions from this single table. Right now, just note it down. I'll explain. You have to discuss some points here. Tell me when it is finished. Vashra, okay, done. Saksham, done. Okay, fine. Can I know this? Give a note, N-O-T. See, you have to remember, some of you can ask me, or you can ask me like this. So where these load combinations will be there. See, if you talk about this dead load live load combination for ordinary constructions, like for ordinary structures, the load combination to be considered is dead load plus live load combination. See this combination, that is dead load plus wind load or earthquake load combination. No live load is acting on the structure. So what is that structure where there is no live load? What is that structure for the design where there is no live load? This load combination is mainly used for the design of chimneys and all, where there is no live load acting on the structure. And coming to these three, dead load, live load, or plus wind load plus earthquake load combination, this load combination is considered for our high-rise buildings. If the building is a high-rise one, we have to consider the effect of wind load also. Now you have to consider something here. Yes, Anindita Bhuvan is asking. Yes, I am coming to that, Anindita. See, if you can see here in this load combination, this wind load or earthquake load combination is there. Suppose in a structure, wind load is also acting and earthquake load is also acting. But why it is considered wind load or earthquake load? You have to remember this. Whenever, you can write it, whenever wind load or earthquake load is acting together in a structure, whenever wind load or earthquake load is acting together in a structure, their effect is almost same, so that we have to consider the maximum of the two. Getting it? Whenever wind load or earthquake load is acting together in a structure, consider the maximum value. Suppose, have you written it? Should I write it here? I write it here. When wind load and earthquake load is acting together in a structure, consider the maximum of the two for the design. Whenever wind load or earthquake load is acting together in a structure, you have to consider the maximum of two for the design. Suppose in a structure, wind load acting is 50 kilonewton per meter, or let's say 5 kilonewton per meter. Earthquake load acting here is around, suppose let's say 8 kilonewton per meter. Which one will I consider for the design? Which one will I consider here in this equation? Will I consider wind load or earthquake load? Will I consider wind load or earthquake load? I will consider the earthquake load. Remember this. First point you have to consider. Whenever wind load or earthquake load is acting together in a structure, you have to consider the maximum of the two. That is, here it is earthquake load. The next point is, our Anindita Bhuvan was asking, why we are considering 0.9 and 1.5. When we will use 0.9 or when we will use 1.5. Write like this. Whenever a reversal of stresses or stability against overturning is involved in the question, consider 0.9 instead of 1.5. You can ask me, what is this reversal of stresses? Right? What is this reversal of stresses? Anyone, what is the reversal of stresses? I told you, for a structure with wind load is acting, sometimes wind load can act in this direction, sometimes wind load can act in the opposite direction, right? So that means the direction of this wind load and earthquake load will vary from time to time. As the direction of load changes, the nature of stresses in this material will also change. Suppose when the load is acting in this direction, suppose the force here or the nature of stress here is tensile. For example, I'm not sure. And when the when load is acting in exactly in the opposite direction, what will be the nature? It will be compressive. So whenever the magnitude of load is changing, the nature of stress or the nature of force inside the member will also change. Then that we are discussing here under the heading, that is reversal of stresses. That's actually the meaning of reversal of stresses. Stress is varying, like from tensile to compression, compression to tension, due to the change in direction of these forces, especially for our wind load and earthquake load. Whenever in the question it is given that reversal of stresses are there, or the stability against overturning is there in the question, you have to consider 0.9 in this table instead of taking 1.5. Right now, these are the 2 points you have to keep in your mind while calculating the design load. Please note it down. After that, we will solve a question. So, what are the load combinations? It was mentioned in the table now. In order to find the design load, as I told you, I will be considering different load combinations. When I consider dead load plus live load combination, the design load will become 1.5 dead load plus 1.5 live load. For our dead load plus wind load or earthquake load combination, the partial safety factors will be 0.9 or 1.5 dead load plus 1.5 wind load or earthquake load. Don't forget the things I have mentioned just now. If the reversal of stresses are involved, use 0.9 instead of 1.5. If nothing is mentioned in the question, use 1.5 instead of this 0.9, right? Considering this wind load and earthquake load, if both the things, both wind load and earthquake load is acting together in the structure, take the maximum of 2. If I consider dead load, live load, wind load or earthquake load combination, the load factor value will be 1.2 dead load plus 1.2 live load plus 1.2 wind load or earthquake load. We have to consider the factor of safety as 1.2, 1.2, 1.2. Not factor of safety, it is the partial safety factor for loads. Considering our limit state of serviceability, for limit state of serviceability, similar to this, for dead load, our live load combination, the load factor, partial safety factor for load will be 1 dead load plus live load, that is 1 live load. For dead load plus wind load or earthquake load combination, the partial safety factors will be again, it is 1 dead load plus 1 wind load or earthquake load combination. And for finally, when you consider dead load, live load, wind load or earthquake load combination, the partial safety factors to be considered here is 1 and here is 0.8 for live load and here it is 0.8 for wind load or our earthquake load combination, right? So remember this. And after calculating these values, we have to consider, after considering these load combinations, I have to consider this maximum value. I have to consider this load combination, this load combination, find a value, we will get a value here. For this load combination, I will be getting a load value. For this load combination, I will be getting a load value. For the design, I have to consider the maximum as per for our limit state method of collapse. And here in limit state of serviceability also, we will be getting a value here, we will be getting one value here, we will be getting one value here, and we will be taking our maximum value among the three for the design. Getting it right? Yes.